For this lesson, we're going to look at implicit differentiation, which is a way of differentiating when we don't have a y that's isolated from x. And in fact, we can actually apply it to cases where y is not even a function of x. We are just going to treat y as if it was a function of x, and we can get some very interesting results. So let's look at our regular method of differentiating. We have y equals 3x squared. Okay, so y is isolated, and we are going to call this now explicit differentiation. We are this is the differentiation we are all so very used to by now. Differentiation. Okay, so we are going to take just the derivative of both sides, so y prime is equal to 6x. We are taking the derivative of our function with respect to x. Okay, so what happens if we don't bother isolating y? What if we have a y minus 3x squared equals 0? Y prime should be the same in this case because this is technically the same function. We've just rearranged it a bit. So here we say that y is not isolated, and we call this implicit differentiation. So what we are going to do is we're going to treat y as a function of x, some unspecified function of x, and we are just going to say, well, if I take the derivative with respect to x, dy dx, and I'm going to subtract the derivative of 3x squared dx. And in fact, I'm treating each piece as if it is a function that I am differentiating, and that's equal to d0 dx. So I get here dy dx, or y prime, minus the derivative of 3x squared with respect to x is 6x equals 0. So I get y prime minus 6x equals 0, and y prime equals 6x. So in this case, this may not have been the most efficient way to do this, but in other circumstances where we have curves that are based on values of y that are not necessarily functions of x. So it could be things that have like an x squared and a y squared, conic sections, anything like that. We can still find a derivative in terms of both y and x by using implicit differentiation. Okay, so let's look at an example. And so we are going to treat y as an unspecified function of x. So we're going to pretend y is equal to some function of x, but we don't know exactly what it is. So what we're going to do is we are going to find the derivative of 3y to the fourth with respect to x. Okay. So this is going to be the same. We're going to now apply the chain rule to this problem. So this is the derivative, and applying the chain rule is really key to any implicit differentiation problem that you're doing. So we're going to say this is the derivative of 3y to the fourth with respect to y times dy dx. Okay, so that is going to be equal to 12y cubed times y prime. Okay. And now we're going to also find the derivative of another combination. So let's find the derivative of 2y to the fifth minus 6y squared with respect to x. So we are going to, again, treat it like the chain. You're going to use the chain rule because we're treating y as some unspecified function of x. So this is going to be the derivative of 2y to the fifth dy times dy dx minus the derivative of 6y squared with respect to y times dy dx. So we're pretending this is some function, y is some function, we just don't know what it is. And so this gives us 10y to the fourth times y prime minus 12y times y prime. So now let's look at a more practical application. So let's take example number 2. So we are going to find the slope of the tangent to the curve at 1, 1. Okay. So we are going to find the slope of the tangent to the curve at 1, 1. So our curve is 3x squared plus 4y squared equals 7. Okay, and so for those of you guys who are not sure, this is a conic section. You can graph it in Desmos and see just what it looks like. And you're going to, when you're doing this, there's going to be the slope of the curve. If we actually take a look at what that graph looks like, you're going to see when you notice that there are going to be multiple points, multiple y values for any given x value. And that's because y isn't a function of x in this case. So there's not going to be a unique y value for an x value. So what that means is the slope of the tangent line is going to depend not only on the x value of the point, it's also going to depend on the y value. So you're going to get not a function for your derivative, you're going to get a relation that uses both x's and y's, and you're going to need to know both the x coordinate and y coordinate of the point you want to plug in. So let's go ahead and differentiate implicitly. So we are going to find dx squared dx plus dy squared dx, and that is equal to d7 dx. So d3x squared, d4y squared. Don't want to forget my numbers there. So d3x squared is going to give us, dx is just going to give us 6x. So we're going to have to use the chain rule on the second piece, which is d4y squared dy times dy dx. And that is equal to d7 dx, which is 0. Any derivative of a constant is always, as usual, going to be 0. So this is equal to 6x plus 8, excuse me, plus 8y times y prime, and that's equal to 0. So in this case, if I want to find this, I actually want to find y prime. So I'm going to have to solve for y prime. So I get 8y times y prime is equal to negative 6x, and y prime equals negative 6x over 8y. Okay, and we can simplify this to negative 3/4 x y. Okay, so we want to evaluate y prime now at 1, 1, which is going to be negative 3 times 1 over 4 times 1. Whoops, not negative 1, just plain old 1. And that is going to be equal to negative 3/4. So the slope of the line tangent to this curve at 1, 1 is equal to negative 3/4. Let's see how to find dy dx in a slightly more complex example. This is going to involve a bit of substitution, and if you have to find a second For example 3, we are going to want to, again, find dy dx. We have x cubed minus 8xy plus y cubed equals 1. So we're going to find the derivative with respect to x of each of these in turn. So dx cubed dx minus d8xy dx plus dy cubed dx, which is equal to d1 dx. So this is going to give us here 3x squared minus, and we're just going to leave this for a second, and we'll come back to it. So this is going to be, because we're going to have to use the product rule, so this is going to be minus 8 times dx dx y, which is 1y, And then this is going to be dy dx plus dy dx times x. This is going to be plus, using our chain rule, 3y squared dy dx, and that's equal to 0. So simplifying all of this and rewriting it with y prime, we get 3x squared minus 8y minus 8xy prime plus 3y squared y prime equals 0. We're going to get everything on one side, and we're going to simplify here. So we get y prime times negative 8x plus 3y squared is equal to 8y. We have a negative 3x squared plus 8y, so we're going to do 8y minus 3x squared. So now dividing, we get y prime equals 8y minus 3x squared over 3y squared minus 8x.